Hello everyone, I'll be discussing the RSA algorithm today. It's a network security algorithm, okay, and it is a full form. RSA is a full form of three people who actually worked for this particular algorithm or framed this particular algorithm, where R stands for RIVEST, S stands for Shamir, and E stands for Adleman. It's a asymmetric key algorithm where we use the combination of two keys, private and public key. So both of these keys are actually framed on the receiver side, right? From the concept that we've already studied as what is a symmetric key. So I've taken this particular scenario over here as Alice and Bob. So Alice is the sender of the message and Bob is the intended receiver of the message, right? Now, whenever Alice wants to send a message, if Alice sends the message in its original form, there might be a lot of people who are trying to watch and attack the network, right? Who might be silently watching the network, waiting for Alice to produce an original message in its original form. So if Alice sends the message in its original form, these people who are trying to listen and attack would get hold of the confidential data or might even corrupt it, right? So Alice, who wants to send the original message, is known as plain text. So since these kind of people exist, okay, right, like the intruders on the network, right? So we cannot send the message in its original form. We need to encrypt the message so that we create a ciphertext which can be communicated over the network without harming the content of the message or getting other people get hold of the confidential message, right? So when Bob receives this ciphertext, he's not actually supposed to process with the ciphertext. He's supposed to first convert it back to the plain text and then use the plain text for his personal purposes, right? So we need to convert this ciphertext back to plain text in the receiver side, okay? And to convert the ciphertext to plain text, we'll be using the decryption algorithm, right? So this is the basic concept of computer networks security, right? So RSA works in this encryption and decryption technique, okay? So first I'll be writing the formula that is used for encryption in RSA and then the formula that we use for decryption in RSA. So the encryption process has ciphertext being created using plain text raised to the power of E mod n. Okay, so this is the encryption process that happens in the sender side using RSA. In the receiver side, we will have the decryption process where we find the plain text to be equal to ciphertext to the power D mod n. So this is the decryption process that happens on the receiver's end using RSA. Now we know what is a plain text, we know what is a ciphertext, right? But we do not know what is E, what is D, or what is even N, right? Now, next up I'll be explaining you the calculations for E, D, and N, okay? So now what happens is all these calculations are related to keys, the private and the public keys. So it happens on Bob's end because Bob is the receiver. So originally what does Bob do is Bob will choose two prime numbers and name it as P and Q. Next up, he'll calculate a value known as N, which will be equal to the product of P and Q. Next, he'll be calculating a value known as phi, which will be a product of P minus 1 and Q minus 1. And then he will choose an integer E such that there are two constraints. he keeps in mind while choosing these integer e that e will be greater than 1 and less than the value 5. Also, the greatest common divisor between e and 5 will be equal to 1, right? After he chooses e, he will calculate d, okay, based on the equation product of d and q will be equal to 1 mod 5, okay, right? So these are the 5 steps that happens on the receiver's end, which means that it is Bob for this particular case. Okay, so I'll be now explaining you an example for better understanding of all these formulas, right? So now I'm taking up an example where Bob in the first step, Bob chooses P and Q. So I'm choosing I as Bob, I'm choosing P is equivalent to 7 and Q is equivalent to 11. Remember, I had told you that P and Q has to be prime numbers. So 7 is also a prime number and Q is also a prime number. Q is equals to 11 is also a prime number. Now I'm choosing 7 and 11. You may choose any other number, but remember it to be a prime number. Next up, I need to calculate n is equals to P into Q, which is going to be 7 into 11, which is nothing but 77. Next, I need to calculate so I'm done with the first and the second. Now I need to calculate 5. So 5 is equivalent to P minus 1, which is 6, into Q minus 1, which is 10. So we'll have 5 is equivalent to 60. Okay. Now next what we have is we need to choose an integer e. Okay, and we had two constraints that e has to be greater than 1 and lesser than 5, right? So that is simple. You can choose any number. That means you can choose any number which is between 1 and 60, right? Now this is first constraint. Okay, now the second constraint says that the GCD or greatest common divisor between e and 5 has to be equal to 1. Okay, now GCD greatest common divisor means the numbers that are the highest number that is dividing both e and 5. All right, so now that means suppose for now I'm choosing e as 5. Okay, so 5, if I choose e as 5, it will satisfy the first condition, right? Because it is between 1 and 60. Now will it be satisfying the second condition? So I'll be seeing whether number 5 satisfies the second condition. So I'm taking e to be equivalent to 5 and 5 is 60. So is equals to, now first I'm writing the common divisors only. Okay, I'm not writing the GCD, I'm writing the common divisors between 5 and 60. So 1 divides both the numbers 5 and 60. Also 5 divides both the numbers, right? So now if you see here, I have two numbers that are dividing 5 and 60, and the greatest number that divides 5 and 60 is going to be 5, which means we do not hold by the second equation, right? So it is false, so we cannot take 5 as e, right? So if you realize what happens in the second equation is the common divisor, the greatest common divisor has to be 1, which indicates that e is a prime number, right? So if e is a prime number, 5 is also a prime number, but 5 does not work here. So here also you have to keep in mind is when you choose e, it should be a prime number plus a prime number which does not have GCD greater than 1, which does not have GCD greater than 1 with reference to the value of 5. Okay, so I cannot choose 5 here as E because 5 is a prime number. Though it is a prime number, the GCD between 5 and 60 is not 1. I need a value which results in 1, right? So when you choose E, please remember that it has to be a prime number, but also you have to keep in mind that the GCD is not greater than 1, or you have only 1 as GCD between 5 and E and 5, right? So now I'm choosing based on these two criterias. Okay, I'm choosing E to be equivalent to 13. You can choose any other number as well, but I'm choosing 13. Okay, so if I choose 13, the GCD between 13 and 60 is going to be 1 because 13 won't be dividing 60, right? So now once you choose E, you need to calculate D. Now when you calculate D, you need to keep in mind that product of D and E should be equal to 1 mod phi, right? Which means, in other words, which means that the product of D and E is 1 greater than a number which is totally divisible by 5. Okay, so which means D into E minus 1 is going to give you a number. This is going to give you a number which is just one number greater than the number that is completely divisible by 5, right? So now how do we calculate that, right? So if I have to show you the calculation for that, so I'm rewriting the condition here. Okay, so if I have this particular condition to be satisfied, we know what's the value of E and we know what's the value of phi. So I'm writing the value of E as 13 here, and I'm writing the value of phi in this particular equation. This is 16, right? Now we know what is the value of 13 and we know what is the value of 60. Now what does the equation say is we are actually playing with the products of 13 and 60, right? So 13 and 60. So the product of 13 should be one number greater than a product of 60. Product means it is completely divisible, right? So what I'm doing is I'm writing the table of 13 and table of 60. Okay, so 13 one times is 13, 13 two times is 26. Okay, so similarly if you'll see there later on, 13 37 times is going to be equivalent to 481, right? Similarly, if I write the table for 60, 60 one time is 60, 60 two times is 120. Similarly, you'll see later on that 60 8 times is going to result you in 480. 480. Now if you see here, I have a product of 13, which is 481, right, which is 1 greater than the product of 60, right, which is 480. Now if I go back, I had told you the product of E should be 1 greater than the product of 60, which means the product of E minus 1 is going to give me a number which is completely divisible by 60. 0 means mod of something is equals to 0 means it is completely divisible, right? So now, did I get the number? I have a number which is a product of 13, right, which is 481, which is 1 greater than a number which is a product of 60 or completely divisible by 60. So 13 into something gave me this particular number 481. So over here also I needed E into D as a number which is 1 greater, so which implies that D is equivalent to 37, right? So a simpler thing that you need to keep, you can keep it as a hint in mind, is D is always going to be, in most of the cases, is going to be a prime number. Okay, right? So now we've calculated D, which is a prime number, 37. Okay, so we've calculated D over here as D is equals to 37. Now, what are these values that we have calculated? P, Q, N, phi, E, and D, right? Now, in the earlier equation, if you remember, I had told you your ciphertext is plain text raised to the power of E, and plain text is ciphertext raised to the power of D. Okay, so that means all this calculation, by the way, is happening on the Bob's end, that is the receiver's end, right? So now what Bob will do is Bob will announce E to all the other parties on the network, and all the other parties who are on the network who's intending to send a message to Bob will use E to encrypt the message. Therefore, you have the formula as ciphertext is equals to plain text to the power of E mod N, which means that E is nothing but a public key. Okay, and similarly, what will Bob do is Bob will keep the value of D secret to itself to decrypt back the ciphertext, that means to calculate the plain text, which will be ciphertext raised to the power of D mod N, right? So this is nothing but the private key. Okay, so now I'm going to take up a new example to explain you the decryption and the encryption process. Okay, so for the encryption part, I'm taking plain text is equals to 5, right? So you have ciphertext is equals to 5 to the power of E, which is 13, mod N, which is 77. You'll see that 5 to the power 13 will give me 26 mod 77, right, which ultimately is going to give me 26. Similarly, on the decryption part, that is on the Bob's end, you receive this particular ciphertext. So ciphertext is equals to 26, right? You need to calculate the plain text based on the received ciphertext value. So you will have 26 raised to the power of D, which we have calculated it to be 37, mod 77. Okay, so 26 to the power 37 mod 77 is going to be 5 mod 77, which is equivalent to 5. Okay, now this happens on Alice's end, and this happens on Bob's end. Okay, so this is the encryption and decryption process for RSA. Now you must have understood everything from RSA, but there might be a slight confusion or slight doubt on how did we calculate 5 to the power mod 77 is equals to 26 to the power 26 mod 77, or how did we calculate 26 to the power 37 mod 77 as 5 mod 77. So next up I'll be explaining you a simple maths where we use this calculation in the encryption and decryption process. Okay, so I'm leaving the example that I did earlier because it has already got the answer, right? You just need to solve it. So I'm leaving it to yourself to solve it, right? How it became 26 and 26 to the power 37 mod 77 is equals to 5. Now how these calculations are done, I'll leave it for you to solve it. I'll do a similar example with a smaller value, and you can use the same technique to solve these two questions. Okay, so I'm taking a smaller example as 88 to the power 7 mod 187. 187, right? So what I'll be doing is, now I'll be first breaking the power of 7 as power of 4, power of 2, and power of 1. I'm breaking it in these 3 units. You may break it in different units as well, right? So now once I break this power, I'm going to write 88 to the power 1 mod 187. Why did I write this? Power of 1 over here. 88 to the power 1 comes from this particular one, right? Similarly, I'm going to write 88 to the power 2 mod 187. Where did I get this power of 2? I am taking it from this 2. Okay, similarly 88 to the power of 4 mod 187, which I am taking it from here. Okay, so now I'll be calculating this in simplified forms. So 88 to the power 1 mod 187 is going to give me value as 88 itself. 88 to the power 2 mod 187 is going to give me a value as 77. That means 88 into 88 is going to give me a certain number. Mod 187 is going to give me the remainder as 77. Similarly, 88 to the power 4 mod 187 is going to give me 132. Right? Now I need to calculate 88 to the power 7 mod 187, which means now I'll be taking 88 into 77 into 132, right, mod 187, which will be equivalent to 30. Now what this 30 that we've calculated is from 3 different powers, which we broke the first equation as. So the first equation will be equivalent to 30. So it is 88 to the power 7 mod 187 is going to give me a number which is equivalent to 30, right? So this is how you calculate This is how you calculate the higher power mod something value, right? So similarly, you can calculate for the encryption and the decryption. Thank you so much for watching.